Hello, Joy.
Good morning, everyone. Welcome to this talk. We're going to talk about spec-driven research for fun and profit. This is just something, an idea I came up with when I was doing some research that was based on reading specs and standards. If you've used IT systems, you've used standard-based systems, pretty much the entire web runs on standards. So it's kind of an interesting area, and I think one that people can dive into in terms of you thinking about what research you want to do next. Before I get started, very bit about me. I've been in IT and information security for a bit over 20 years now. I'm pen testing and various other things. These days, I am a senior security advocate for a company called Datadog. If you've never heard of us, we are a SaaS-based provider of monitoring, observability, and security. So this talk is not about Datadog. If anyone wants to talk about that sort of thing afterwards, happy to do so. I generally focus on container security. Anyone who's seen any of my talks in the past probably realizes this. Docker, Kubernetes, that kind of thing. And I have had the opportunity to present at a reasonable number of securities. I looked up by my desk, I've got my lanyards, and I got there, the left, the one in the front, Security 1, 2011, and then the Security 2 to 3, and the 2018 one. So I think I've not quite spoken to the most securities of anyone, but Graham Sutherland and Paco Hope used to beat me, but they're not in this year, so I get one up on them. So I might get my title back. Anyway, let's get on with the talk. So, why are we interested in specs and standards? Why is this something we want to know about? Well, pretty much the entire internet and various other systems run on standards. These things are decided by when a new area of technology comes along and vendors are getting involved in it. They start thinking, well, we want our systems to be able to talk to each other, right? We want everyone to be able to interoperate. To do this, we need to agree how we're going to handle data, processes, protocols. So they come up with a standard. The standard bodies, there's lots of them, depending on the area of technology, will typically say, okay, there's a new area of technology. We need a standard for this. Let's get one going. The reason why, in addition to like kind of obviously altruistic, we want to work together, big companies, big end users of technology like standards, right? There's this dreadful fear in enterprise of what's called vendor lock-in. So I buy something from one company, they're the only people that make it, and then if I ever want to leave, I'm in trouble. And when the contract negotiations come around next year, they know they've got you because you can't move. So end-user companies like standard-based tech because they hopefully don't have that lock-in. They can move to anyone else who implements the same standard. So there's a good reason for this to happen. The other thing is typically sometimes when a technology becomes popular, maybe some vendor starts something, right? And everything takes off and everyone's happy. They go, well, after a while, people aren't going to trust us as it's just our tech. So we'll donate our technology to a standards body. So you'll see a lot of people, when they're the kind of early adopters, they donate their work to standards bodies who then carry it on. And when you have a standard, you need a specification. You need something detailed, low level, that everyone can read and go, okay, I understand if I implement what's written here, I will be able to interoperate with everyone else who's done the same thing. So that's kind of where specs and standards tend to come from. So how do these things get written? Right? How do I get from, we have this idea of a standard to a detailed spec? And typically, and I want to generalize a little bit here, typically this is done by lots of people, senior kind of IT architect types from big companies and academia who get together into a committee and sit down for lots of time writing a document. And if you think about what their interests are, you start to get an idea of where we might have some fun from a security perspective. All of these companies want to make sure that in the standards, everything they need for their software to work. So there's lots of incentives for them to put more things into the standard, more use cases. Because they've all got complex big customers with complex big use cases, and they want the standard to reflect all of the things that they want to do. Right? So this tends to lead to standards. If everyone's ever read a standard, you kind of the idea there's a lot of kind of complex stuff in there, and that's why it happens, because there's a lot of interest in people making these things big and wordy and covering every possible use case. So they tend to be bigger rather than smaller. So that starts to get the idea of what we're interested in. So I'll give an example, just to kind of make this a bit real. That was a little bit abstract. I'll talk a little bit about a thing called SAML. If you're in enterprise IT, or if you're ever using an enterprise IT system, you will have come across SAML, Security Assertion Markup Language. The idea of this is it allows authentication providers to talk to web applications in a way to say, here is the credentials for this user, you can believe them when they say they are who they say they are, and log them in. And the idea is that lots of different systems can talk to each other using SAML. SAML's been around for quite a long time. It came up in the kind of mid-2000s as a spec. And it's all written in XML because back in the mid-2000s, everyone thought everything should be XML. Luckily, we don't do that anymore. But it's still there, right? And I use SAML every day, right? I use Google as my identity provider. Every system I log into tends to be logged in via SAML. So it's a very heavily used piece of tech. And SAML, well, this is a spec, right? The spec is 96 pages long. This is one section of the spec, section 2.4.1.3. I'm not going to try and go through this. The idea is to give you an idea that this stuff gets a bit complicated. That's one section. Now, imagine you're a developer. You have been tasked with writing a SAML implementation, and you have to make sure that it does exactly what the spec says. You have to read 96 pages of that and write code that works exactly as that spec says it should work. If you've ever coded, you're probably going, oh, dear Lord, no one will ever want to do this. But this is interesting from our point of view because of there's lots of security truisms out there. I don't actually subscribe to all of them, but I do subscribe to this one. Me and lots of people. Complexity is the enemy of security. The more complex a system is, the less likely it is to be secure. The reason is, imagine, I'm guessing some people who have written programming code before. When you write code, you're trying to keep in your head, what's my code flow? What is all the data going in and out? What are all the formats? The more complex it is, the harder it is for you to keep that in your head. So the more complex you are, you're going to make mistakes, things are going to leak through the cracks, you're going to end up potentially with security problems. And then you imagine being someone implementing this and going, there's absolutely no chance that any one person is going to keep that in their head all the time. So you'd have big teams doing this, and when you have big teams, then you have problems of, oh, I thought this meant that, oh, I thought this meant this other thing. Great. As a researcher, I'm going, well, that's great, because if you make mistakes or you don't understand it, there's opportunity for security flaws. So complexity is very much the enemy of security, and that's why I think specs are interesting, because specs are complex. Things based on specs are inevitably complicated, therefore they're inevitably not secure, as a rule. In the case of SAML, I had a quick look through the CVE database, and I said, what is that? Did that turn out to be true in this case? 247 CVEs say yes. There are 247 CVEs that mention the word SAML. If you look through some of them, they're typically implementation flaws. So some provider took that spec, tried to write code that implemented it, and missed something. I'm not surprised. But from a research point of view, that meant that 247 researchers got a nice CV to their names and did some interesting research just by reading one specification. The two types of flaws you get, typically when you read through some of these, one is ones that are an implementation mistake, right? So someone read this, made a mistake, fine, we get a bug. The other ones which are interesting is, think about the standard writing process. A committee of people all got together and agreed that. Do you think they got the spec 100% right? They didn't leave any edge cases that weren't accounted for? They didn't leave any undecided variable bits? The answer is no. Of course they did. Spec issues are even better because you get all the implementations at once. So if I get something wrong in the spec, I can go around and get bugs in every single implementation of that software. Here's a SAML, 247 CVEs. So it's fair to say this does happen. So that was kind of like the theory, right? The theory is, or my idea, hypothesis, is that specs lead to security flaws. So let's look at a worked example of this. And this is a really simplified kind of process that I went through when I was doing some research. So, I'm not a full-time researcher, by the way. This is more something I kind of do in my weekends for fun. I know. Read the specification. Right? First thing, got to read the spec, work out what's going on. Find something interesting looking. And I'll talk about how I found something interesting looking. Get an implementation, so get software which implements the specification, because that's kind of the stuff that'll have the bugs in it. Run the experiment, design it, run it, success, failure, back to the start. Pretty simple research process. So the way I did this, the one I want to talk about is a thing called the Open Container Initiative, OCI. So if you've used Docker, you've used Kubernetes, you've used Podman, you've used containers, I guess most people will at least use some level of containers, they implement this thing, the specs written by OCI. These were one of the donated types. So Docker wrote these specs in the early days of containers. They then said, well, people won't adopt this stuff if it's just us, because they'll be worried about vendor lock-in. So they donated them to a body called the Open Container Initiative, which is under Linux Foundation. And they now manage, develop, and run these specs. There's the image spec. So when you pull a container image, it's part of the OCI image spec. That's the format. When you run it with Docker, Podman, Containerd, that is the OCI runtime spec, so anything which runs containers. And then you pull it from registries that are the OCI registry spec, right? So 3 specs. I'm going to look at the image spec, right? The image spec was the first one I looked at, because I thought, well, that's kind of easy. I use lots of container images. Let's have a look and see what the spec says. So first thing to do is read the spec. Luckily for me, it's not 96 pages long. I'll be honest with you, if it was, I wouldn't have read it. It's more like 15, 20 pages. So this one wasn't horrifically, hard to look at. If you're starting doing this, pick a simple specification. Don't do some of the old XML stuff because your head will explode. The modern stuff is a bit kind of nicer. So I read the OCI image specification. It's available online. Pretty much all specs are available online because obviously you can't write implementations if you don't make the spec freely available. So the information is always there for you to read. And I ended up, it's only a little bit small, I ended up drawing out this. So a good way to do these things is visualize what you're doing, or I like to try and visualize what I'm researching. I've read a long document. Let's try and visualize. This is all the different parts of a container image and how the specification says they work, right? So it says an index contains one or more manifests, which is a type image manifest, which contains config, image layer, subjects. And I basically looked through this and said, right, where is something that could be interesting? Where do I think there's something which might be a bug or might have something interesting to play with from a security standpoint? And so I went to look for an interesting part. And the interesting part I came on was descriptor. So I noticed there were lots of arrows all pointing at this one thing. So I thought, okay, that's interesting because this is used throughout image specs. So let's hone in on that. And I said, what is a descriptor? And it turns out when you're describing a container image that's OCI format, everything is of type descriptor. Right? So you can put anything which is part of the descriptor type into any part of the spec. Okay, cool. Let's have a look at that. So I looked through all the different things I could have in a descriptor, and I said, well, what could I play with? And I found URLs. Now, as soon as I saw URLs, I then said, this is potentially very interesting. One, I've never seen a URL in a container image I've looked at ever, so that's weird. Two, if I see URLs, I think of a couple of things. If it's a URL, that means that systems might make network requests, right? Because what are URLs? They're things you request online. So if this thing can have URLs in it, does that mean it will make network requests as soon as I put one of these in? That's an interesting one to look at. Also, URL parsing is a common core source of security vulnerabilities. URLs are actually surprisingly complex. If you ever want to dig into quite how weird URLs can be, go and read the guy who writes curl has written some blogs about exactly how weird URLs can be. If you think they're just http:// no. Way more complicated than that. So there's potential parsing bugs as well. And then there's potential for things like server-side request forgery. So that's a bug where I can make some system make network requests on my behalf in a way that's more trusted than I would be. So there's lots of things. As soon as I see URL, I'm interested to go, okay, that's fun. Let's go and play with URLs and see what happens. So I thought, okay, URLs. Let's look at that. And so the spec describes it. And this is what the spec says about the URL field, because you can find out and say what it's meant to do. So this is kind of fairly simple. It says this optional property specifies a list of URIs for which this object may be downloaded. Each entry must conform to an RFC. Entries should, right. There's some, I've highlighted, actually I missed one. The interesting thing for me were optional should and may. And you notice they're all caps. If you're wondering why they're all caps, there is a spec which describes how you write specs, or actually there's several. There's a spec RFC 2119, which says what these words in caps mean. And in the case of optional should and may, it says this: if you're implementing this, you don't have to do this bit, but you can, right? So they don't have to put this in. As a researcher, I like optional may and should for a couple of reasons. It means that different implementations might handle it differently. So I might get bugs where one implementation does it this way, one implementation does it a different way, because it's should and optional. It's also code that won't be heavily tested, right? As a researcher, you're looking for stuff that people missed. I'm looking for things that people didn't look for. Things that are optional tend not to be in fully test suites, because why would I test that as optional? I never do it. Okay, cool. I'm going to look for anything which says optional in a spec. So now I've got a URL, and I've got the fact that it's optional. Cool. This sounds like at least worth looking at. It's at least worth playing with. But in general, if you're looking through specs, look for those words. And you'll find them lots of places. Specs are amazing for like conditional weird things that no one ever uses. But typically when developers are writing implementations, they'll just put everything in there. Because they're like, hey, at some point in the future, someone might want this. I might as well write the code while I'm writing it. So, what can we do with this? So then it's like, well, what would this mean? Say I do this and it would actually does something. What are the security vulnerabilities I might find? Well, one, I might be able to create tracking, right? If I'm successful in embedding a URL that is then pulled every single time someone gets this image, I can track their use of the image. So I can start, people don't expect that. They don't expect an image to track you and provide telemetry. So that's interesting. Maybe I can do that. I might get SSRF, right? What can I do if I can make it pull a URL under the control of the container engine that's running this container? potentially that. I might also get, I didn't actually put it up here, I should have done, URL parsing bugs. So I might get an actual vulnerability in an implementation where it parses the URL, I give it some weird URL with lots of different parameters in it, and it complains, crashes, or maybe actually does something like, gives me access to the system. So there's some possible things there. Get implementations, right? I need software that actually implements this to work out whether this is really a problem or just something in the spec that's kind of interesting. So in the case of OCI, there's quite a few different implementations you can get your hands on. First one's container runtimes, right? Container runtimes are the things that run containers. So when they're going to pull my images, they're going to run them. These are the things I want to actually get down and play with. Luckily, it's all open source, super easy. If you're doing some specs, you have to watch because a lot of it's implemented by proprietary software. It can be harder to get implementations, but pretty much everything in container is free. Docker is the original OG software that everyone has used. Containerd is actually used by Docker, but also works standalone with a program called Nerdcuttle, for reasons, I don't know why they call it that. And Podman is Red Hat's. Red Hat doing everything in containers their own way because they're Red Hat, and they have their own tools for everything. I can then get container builders, things which can build images. So if my research is around container images, I need to have tools which build images. Docker BuildX is Builder. Again, Builder is Red Hat's one. Docker BuildX is the new version of Docker's Builder. Container tools, Scorpio and Crane. There's some tools that muck around with images. They move them, they translate them, they upload them, download them, inspect them. So they're interesting as well. And container registries. I need to put my images up somewhere and have them retrieved. There's loads of these. And they all pretty much implement these OCI specs. So Docker Hub, GHCR, Key. There's also the cloud providers have got their own registries too. So there's lots of opportunities here. And these are the ones I looked at. There's probably more. But those are the ones that kind of a good starting point. So design experiment, right? I now have a thesis. I have this idea. URLs could be interesting. I have some software. Let's go and things to play with once I've played them. So how do I actually get to the point of designing an experiment? So this is what a container image actually is. If you've ever done Docker run something and you've actually run it, container images are actually just tarballs, which is kind of nice if you want to play around with them, because you literally just save them out of Docker and untar them. It's literally just tar. So it's nice and easy to do. And this is what they actually look like when you get in there. Index and manifest JSON and OCI layer are just, this is how this container image is kind of laid out. Everything is in these blobs. The blobs are all identified as SHA-256 hashes. It can either be a manifest that describes the image, it can be the configuration of the container image, or all the files. But everything just lives as these blobs with the kind of SHA hashes. And the SHA hashes are interesting because that's how they verify you haven't mucked with it. If you mess with these things, the SHA hash changes. As soon as you change one character, that SHA hash completely changes. So that's what you end up having to kind of like, where all your information ends up being. So I got one of these. This is a really simple. I always recommend when you're doing something like this, start with the simplest possible version of the software. You don't want to make it more complex if you're doing experiments. This is the simplest possible image. This is just BusyBox. Literally, very simple image. And I got the first file, which was the index manifest, and it looks a bit like this. You can see it describes the config there, and it describes the layer of the container image, but that's the correct how the manifest is laid out. What you will notice is there's no URLs. And I looked at quite a few images that I got from various registries. None of them use this URL field. It's totally unused, but it's available. So what I did was work out where do I put a URL. And I ended up working out, you put it there. It's a JSON file, so if you know JSON format, it's pretty easy. I basically added a URL to that config section. And what I did was I got a domain name, which I control, logs.puntland.uk, actually using one of the many domain names I bought, which is nice to do, rather than just leave them waiting there to get renewed in 2 years' time. But yeah, I actually used this one, so I used log.puntland, and I basically put a file that had the SHA hash name of the same as the config, right? So that these things matched up. So that has the exact same content as there is there, so that it doesn't complain when it actually pulls it. And I said, okay, let's put that in. And then I bundled that back up and copied it back up to container registries. So I modified it, got my experiment, got my URL in there, and I sent it up to container registries and then see what happens. A little quick aside, if you're doing any testing around web stuff, so around SSRF, you want like test something where you want a reliable URL that you control. It's the best way of doing SSRF testing or any other kind of HTTP testing is get a URL you control and you log, because then when you can tell your experiment's working. Because when you're doing blind experiments, it's really hard to tell if it's actually working or not. Get a URL you control. The way I do this, I've got a little very cheap VPS running Caddy. Caddy is a reverse proxy software and a web server software. It's very, very flexible. This is the config section that I used for this experiment. I would recommend if you're looking into that thing, look into Caddy. One of its best tricks is if you give it a valid domain name, you can just say in the config file TLS, and it'll go away to let's encrypt, and it'll get a valid certificate, and it'll bring it down. So you don't get TLS errors, because a lot of software these days will barf out if it gets a TLS error. Caddy does it all for you. You don't have to worry about how certificates work. Really, really handy. So if you're interested, I've got a link at the end for some more info on Caddy, but definitely just as an aside, would recommend. Run experiment. Okay, we've now got our experiment. We've got our image that we've bundled up with a URL in it. We have got our implementation software might implement this. Let's run our experiment. So what happened? Well, what happened was this is my Caddy log file, and what I found was that when I was pulling the images, not even running them, just pull it down to a host with some of these container tools, I would get a ping. And the bits I've highlighted are very handily. What the software does is it tends to tell you in its user agent exactly what it was that pulled it. So it tells you the software name, so I know exactly which tool it was that triggered it, and tells me the software version, which is kind of interesting because if there's ever vulnerabilities in that software, I get kind of told in advance, which is nice, because I get to know what versions are running. So I got lots of different pings depending on the tools I was using, but that was useful because then, right, you could prove this is working. Right, I know this is now done its stuff because I can tell it wasn't just random people pulling it. I did publish a blog about this, and I started getting weird hits from various people who are obviously clicking links in or copying the URL out. Like, thanks for that. But you can tell the difference because it's the ones that I think should have good user agents on them. So, success or failure. Well, in this case, I got my pings. This is kind of what I was going for. This is the outcome I looked for when I did this. It looked a bit like this. And there was a couple of interesting things. Docker never ever pinged. So despite Docker supporting OCI images and being the tool most people use, it would never pull the URL. My theory is there that what Docker is doing is it's converting it to it had its own proprietary format that existed before OCI. I think when it's loading an image, it's converting it back to its proprietary format and just ditching the URL, which is interesting. Containerd, Pod, and Scopio, they all ping quite happily. And all of them support OCI, even Docker Hub, which is, again, kind of built on the older tech, it supports OCI images. So it worked, this image worked in every one. In terms of the outcome, I did what every hopefully good ethical security researcher would do at this point, and I reported it. So I said, this is something which is in your spec, but it has some unintended side effects. Right? Essentially, I can now build an image that will track any user of that image. People who run containers probably don't think that's something that can happen. So it's unintended functionality. It also has the risk of blind SSRF. So if I give you a crafted URL and you run my image, I can make a request to anywhere in your infrastructure. Is that a security problem? Well, it's not right. It's pretty niche, though. I'll be honest and say I don't think that's something everyone's got to worry about, but it's definitely not intended. It's not something that should be happening. Basically, they said, yep, we recognize that is a security issue. It's not something that's ideal. However, it's in the spec, and it's not that high risk, so fundamentally, we're probably not going to change it. So, happy how this still works. If you want to play with this, I don't think they'll ever fix this, because it is part of the spec. So, to fix it, they would have to remove that from the spec, and whilst I don't think it, and this is one of the other thing about specs, is once it's in the spec, it never goes. People never remove things from spec, they add new things to specs, but they almost never remove things from spec. So that behavior will work forever. So if you're ever in a circumstance where you need to track someone using a container image, I can pretty much guarantee this will always work, if they're not using Docker. Other outcomes, I learned a lot about the OCI spec. This is probably the best reason to do research, if I'm honest. It forces you to learn the low-level details of how stuff works. I now know exactly pretty much how to build container images from scratch with text editors and tar, which I did not know before. So I learned things, which is always great. I also had some fun side effects. I was playing around tarring up my image and then trying it out on various tools. And I found that if I used the tar command basically a little bit differently, some vulnerability scanners stopped recognizing the image. So Docker would still run the image quite happily, but vulnerability scanners would, that's not a valid image, I'm just not going to do anything with it. So again, that's another potential security side effect. I could bypass vuln scanners, depending on how I construct my image in tar. I reported that one. Turns out it's some sort of weirdness in the underlying library. So it will get fixed, but probably no time soon. I also found an image that some container tools will run while others can just ditch it. So I've got an image that Docker will run quite happily, because it doesn't know anything about URLs. But if I put an invalid URL in there, so if you put that URL and you basically make it an invalid URL, Podman and Containerd will go, that's invalid, I'm just going to ditch it, I'm not going to run. So again, you can imagine a circumstance where maybe, for example, a security check is done by something running Containerd, and then the container itself runs using Docker. It'll bypass the security check, because the security check says that's not invalid, that's not a valid image, that's not going to run. Docker says, yes it is. I'm quite happily going to run that. So this is where implementations and differences in implementations can be kind of interesting. Not going to happen every time, but I can imagine that being something that occurs. Further research. Other good thing about research is it always leads to more research. I'm far from finished on this one. Other things I was thinking of doing, or if anyone else is thinking, wow, OCI looks super fun, I'm going to do research on that. Things you could look at. Wider OCI tooling. Things get and parse and look at container images. There are websites you can get that will do things like inspect images. Well, I'm embedding URLs. Potentially, will that do things like that cause them to get it? There's scope there. How do they handle URLs? Another element in that descriptor thing is data. And it basically just says this can contain data, base64 encoded data. But it's not super well specified how container runtime should actually do handle that. So what happens if I put a huge data section? If I put gigs of data into a config section, will it crash? Obviously, when you get into crash bugs, be a bit more careful with third-party systems. I wouldn't go uploading gigs of data in a config section to a public registry, because if you break it, whilst technically you'll be okay, I wouldn't want people receiving it to that call. So there are potential to look there. There's other elements. There's related specs. So the runtime spec and distribution spec, they dictate how you run containers and how you store containers. So you can look there as well. And also specs, as I said, they change. So specs, new versions of specifications will come out all the time. OCI currently writing version 1.1. It's got some new features to handle things like container signing. The way container signing is handled at the moment is pretty hacky, if I'm honest. So this will actually improve that as well. So there's new versions of spec, which obviously, new potential for problems. More information, I'll put these slides online on Twitter afterwards and Mastodon, but just some other ones I would recommend. That post there, Demystifying Security Research by research from NCC. It's a really great post on the process of research and like how it works. Well, I recommend that. I've written up this, if you want more on this particular vulnerability, I've written up that vulnerability and how you do it. And then also, if you want some more stuff about Caddy and how to use Caddy for testing, I've got a blog there for that as well. It's easier to read the blog than just hear a talk. Questions? How much for questions have we done? We've got a couple of minutes for questions now, or otherwise, email, Mastodon, Twitter while it's still up, is available as well. Any questions now? Feel free to contact later. Yep.
When you're talking about specs and that, is this something you think you're going to benefit students rather than the fact that it's a software that you're trying to understand the spec and attack that?
Yeah, I think it's a great way of doing it because, as I said, it benefits as an approach because you can do it in a kind of fairly structured way. You can take a spec, especially newer specs, because the older ones, like the 2000s ones, they've been pretty heavily, attacked. But there's always new specifications coming out in the area I'm in, cloud native. People are specifying cloud native. There's a lot of stuff around there. So yeah, as a kind of approach to research, just going through it, looking for every may, should, optional, must, and then just trying out that process. Right? Just run through the process of get implementations. What happens if I do something weird to X? Put lots of data in it, change the format of data. One thing that's kind of, another thing that you can find interestingly in implementations is some languages where you get code written in different languages. Containers almost always Golang, but some people write things in other languages as well, like Rust, C, whatever. You find weirdnesses in things like how they handle fundamental data. So Golang is very, very strict on IP addresses. If you give it one of those kind of weird formatted octal or hex IP addresses, it just goes, nah, that's not valid. Rust and C will go, oh, that's a completely valid IP address, I'll act on it. So there's lots of fun there to be had as well, and just looking at an implementation written in one language, implementation written in another language. These languages do things differently. That's going to introduce potential for bugs. So yeah, I think for students it's a great idea to pick a spec and dive in, and even if you find no fun bugs, you'll still learn something about how that technology works. Any other questions? Fantastic. Good stuff. Thanks very much.